Hi everyone. So in this video we discuss the strategy of clipping gradients, which is mainly used to deal with the exploding gradient problem. And this problem is very evident or happens a lot with recurrent neural networks, much more than normal feed-forward networks, even feed-forward networks that have the same depth as the computational graph corresponding to the recurrent neural network when unfolded, right? So even if you have a recurrent neural network, after you unfold the computational graph, let's say it becomes a 100-layer network, right? The deep forward network that has the same depth, that's 100 layer in depth, would have a much lesser chance of encountering that problem, right? Let's think of the cliff phenomena that we discussed before. So what happens here is that with a very short move in terms of the parameter updates, I move to a new region, right? So I'm up the cliff, and then the gradient direction will change, right? So when I'm up here, the gradient direction is like this with a very large magnitude, right? So here at this point, very large gradient, right? Very large G. In terms of magnitude, right? So the gradient changes and then the magnitude becomes very big. Now, as the step size for the parameter update corresponds to the gradient magnitude, so I'll move by a large step. And hence, I will undo a lot of steps that we have done before, right? So let's say I move somewhere here, right? And then I have to move all these steps until reaching here. Right, so that could slow training because you could get into these loops where you undo a lot of steps by jumping off cliffs, right? So in these cases, you really want to normalize the gradient, and there are many ways to do that. One strategy is to clip the gradient. By clipping the gradient, mean clipping the gradient norm, but typically you want to maintain the gradient direction. We will discuss the different variations of doing clipping gradients, but before, let's highlight this point, right? So for a feed-forward network with the same depth as the unfolded computational graph, this phenomena is less common. Why? Because in a feed-forward network with the same depth as the unfolded computational graph, the parameter updates are independent from the parameters in the different layers are typically independent or at least different from each other, right? So they are less likely to be in the same direction, like to be all exploding or all vanishing, right? Actually, if they are really independent, then they are more likely to compensate for each other. And there has been a lot of interesting experiments that show that this jumping off cliffs problem is a much more mild problem in feed-forward network than in recurrent networks. Because in recurrent networks, it's the same weight matrix raised to a large power. So it's the same values raised to a large power. So these are not independent realizations of even the same distribution. It's the same realization, the same value for the parameter matrix raised to a large power. So it makes it more likely to have exploding as well as vanishing gradient. In the next video, we'll discuss the vanishing gradient problem, the strategies to deal with it. Here we focus on the exploding gradient. Then how is the gradient clipped? You could think of, basically you take the gradient of the mini batch for all the examples. That's the gradient that is used for the parameter updates, right? Now, one strategy introduced in this paper here, Statistical Language Models Based on Neural Networks in 2012, is based on clipping each element independently. And this is computationally easy, right? So each element in the gradient vector is clipped to a maximum value, meaning if it passes the maximum value, then we threshold it. We set it equal to the maximum value. Now, the problem with this is that basically I change the gradient direction when I do this. So the right way to do it, the more correct way to do it while keeping the mini batch gradient direction, is to clip the norm of the gradient as a vector, right? So if the norm of the gradient is above a certain threshold, then basically we set it equal, we divide by the norm and we multiply by the value of that threshold. So we set the norm equal to that maximum threshold. Now that strategy, that second strategy, would maintain the direction of the mini-batch gradient, but it will not actually maintain the fact that the mini-batch gradient is an unbiased estimate of the true gradient. So it will no longer be the case that the mini-batch gradient is an unbiased estimate. Here we introduce a bias based on that heuristic of the norm clipping, because of the simple fact that averaging the norm clipped gradient from many batches is not equivalent to clipping the norm of the overall gradient. So, and that's actually a very important point, and it's important in multi-GPU systems where you train using multiple GPUs and the batch is divided across the different GPUs, and then you aggregate them and do the parameter update. You aggregate the gradients. So in this case, you really have to clip the norm if you want to do it correctly without introducing, if you want to do it correctly, sorry, then you have to aggregate first and then clip, right? And then clip the norm, which could introduce a delay in the computation or slow the computation, because you cannot really parallelize this clipping thing. But interestingly, the empirical evidence so far points to basically concluding that it doesn't matter much. So even when you clip element wise, it turns out to work well, right? But you should be aware that this is really changing the gradient direction. Now, even more interesting than that is that if the gradient explodes to the point of numerical instability, it gives you an infinity. And when you are implementing it, the programming environment gives you an inf sign. Then actually moving in a random direction, having a random step instead of that exploding gradient, tends to work well in practice, right? So it really, the key is that what matters in practice is to avoid these exploding gradients, even when you replace them by a random step, not necessarily clipping the gradient and maintaining the direction. And that's probably why it doesn't matter much if you clip element-wise or if you clip the norm. But still, this is the empirical evidence so far. The concrete justification is that you should clip the norm of the gradient, and you should be aware that this is rendering the mini-batch estimate of the gradient a biased estimate. It's no longer an unbiased estimate. Sounds good? Thank you. So next video, we will discuss the other problem, the vanishing gradient, and how to deal with it. Thanks.